Alright, section 3.1 is quadratic functions and models. On your last test we went over linear functions. Now we're going to look at quadratic functions. These are the objectives that we're going to cover in this unit. We're going to learn some basic concepts about quadratic functions and their graphs, learn how to complete the square and apply the vertex formula, graph a quadratic function by hand, and then solve a couple of application problems. So some basic concepts. Recall that a linear function can be written as f of x equals ax plus b, or you could write mx plus b, where m would be the slope. What makes this function linear is the fact that x is raised to a power of 1. In a quadratic function, you have x being squared. So you could have f of x equals 3x squared plus 3x plus 5, or g of x equals 5 minus x squared. Here you have both an x squared and an x term. Here you just have the x squared term. What makes the function quadratic is the fact that the x is being squared. Typically our quadratic functions will be written in this form: ax squared plus bx plus c. This is called a quadratic function. The graph of a quadratic function has a parabolic shape. That means that it's U-shaped, and it's either going to open up like this function here, or it's going to open down. The sign of the leading coefficient is what determines if the function opens up or down. The leading coefficient is what x is being multiplied by. In this case, that would be a. Whatever the x squared is being multiplied by is the leading coefficient. If that leading coefficient is positive, your parabola opens up, and it has this minimum value at this low point that we call the vertex. If your parabola opens down, then you have a maximum value at this point that's called the vertex. The vertical line that passes through the vertex is called the axis of symmetry, and we call it that because if we were to fold this graph in half along this dotted line here passing through the vertex, the left half and the right half would match up perfectly. So we have symmetry about that line. X equals whatever the x value of the vertex is. The leading coefficient not only determines whether or not the parabola opens up or down, it also determines if it's wider or narrower. Our parent function here would be this blue graph, y equals x squared. If we have a number bigger than 1 that x squared is being multiplied by, that parabola is going to be narrower. It's going to open narrower than just your parent function of y equals x squared. If you have a proper fraction between 0 and 1 that x squared is being multiplied by, you're going to end up with a wider opening on your quadratic equation. So that leading coefficient determines a lot of things, and it's important to identify what it is. In example 1, we're asked to identify the function as linear, quadratic, or neither. If it's a quadratic function, then we want to identify the leading coefficient and evaluate the function at x equals 2. Does a represent a quadratic function? Yes, it does. What is it that makes this a quadratic function? The fact that this is squared. What would our leading coefficient be here? It's 9, because that 3 is being squared along with the x. So if I took care of squaring that, I would end up with 9x squared minus 2, so the leading coefficient here would be 9. Now we're asked to evaluate this function at x equals 2. That means that I want to replace x with 2 in my function, and I'm going to find f of 2. F of 2 is going to be 3 times 2 squared minus 2. 3 times 2 is 6, and 6 squared is, and 36 minus 2 is, so f of 2 would be 34. What that means is that we have a point 2, 34 on the graph of this quadratic equation. Anytime you plug in a number for x and solve for y, what you're doing is you're finding a point that's on the graph of the function. Is b a quadratic function? Multiply. This is, if I distributed this 2x squared, this 2x, what I would have is 6x squared plus 2x. Now, is this a quadratic function? It's easier to see once you multiply. It is a quadratic function. What is our leading coefficient here? It's 6. And now we need to find g of 2. This is our function g. G says we're going to take 2 times something and then multiply that by 3 times something plus 1. That something in this case is the 2 that we're asked to plug in right here. And that's going to give us 4 times 6 plus 1 is 7, and 4 times 7 is 28. So the point 2, 28 would be a point on the graph of this quadratic function. Is c a quadratic function? H of x. Is this quadratic? No, it's not, because another way that I could write this is x raised to the negative 2. Do y'all remember from your previous algebra classes that if you have a negative in the exponent, To make that negative exponent positive, you just move that base to the other side of the vinculum, that fraction line. X to the negative 2 is not quadratic. This is actually a rational function. Alright, example 2 tells us to use the graph of the quadratic function to determine the sign of the leading coefficient, the vertex, and the equation of the axis of symmetry. Then we also want to give intervals where the function is increasing and where it is decreasing. Using y equals ax squared plus bx plus c, I'm going to refer to the leading coefficient as a. The leading coefficient a, is that going to be positive or negative? It's negative because this parabola opens down. The way you can remember it is negative is sad, so sad is frowning. If you're a negative person, you frown. If you're a happy person, you're positive and you smile, and it looks like a smile. It's corny, but it's the corny things that help us remember stuff, right? This is going to be a negative leading coefficient. Where is the vertex? The vertex is this point right here. The vertex will always be an ordered pair, so what would that ordered pair be? 2, 3. And then the axis of symmetry, I don't just write 2, it's the equation of a vertical line. How do we write the equation of a vertical line? X equals 2, so that would be this line right here. Then the other thing we were asked to do is identify where the function is increasing and decreasing. So this graph would be increasing on the intervals from where to where? Negative infinity to 2, because we're going up as we move from left to right, and we're increasing at that point, and then it's decreasing on the interval from 2 to infinity, because when x is equal to 2, we start going down with this graph. The increasing and decreasing is read with respect to the x-axis. We've identified that the axis of symmetry is right here at 2. That's where our graph switches from increasing to decreasing. Would this vertex be considered a maximum value or a minimum value? A maximum. The cool thing about quadratic equations is they always have a maximum or a minimum value depending on whether or not the parabola opens up or down. And we're going to use that to solve a bunch of application problems. Okay, maybe not a bunch, but a few. There's two forms of the quadratic function. The first form I've given you is the general form, and that's the one that looks like this. This is the general form. In the vertex form, you can quickly identify where the vertex is. The parabolic graph of f of x equals a times x minus h squared plus k, where a is not 0, has a vertex at hk. This negative here is part of the formula. This is called the vertex form. Our x value is going to be the opposite of whatever this is right here, so it's just going to be h and then k. The graph would open up if a is positive and down when a is negative, because a here is the leading coefficient. The vertex of the graph, when it's written in this general form, can be found by using negative b over 2a to identify the x value of the vertex, and once you know what x is, you just plug that number into the function to get the y. Have y'all seen the quadratic formula? X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. How we get this x form, or this x value of this vertex, is we just take the front part of the quadratic formula. So hopefully by tying this to something that you're familiar with, it'll make it easier for you to remember how to find the vertex whenever your quadratic equation is written in this general form. In this form, it's easy to spot, not so much so when it's written like this. This is the formula for finding the vertex for getting the x value, and once you know x, you just plug that x into the function to get y. In example 3, we're asked to write the vertex form for the graph that's shown. This would be easier if we first identify what the ordered pairs are associated with this vertex. This vertex is going to be where? What are the coordinates of it? Now, if we use the vertex form of the function, f of x equals a times x minus h squared plus k, I have numbers that I can plug in for h. The only number I don't know here would be a, so I would have f of x equals a times x minus negative 1 squared plus negative 3. When I clean this up, what I would write is a times x plus 1 squared minus 3. Notice in the vertex form we use the opposite sign here because that negative is part of the formula. So our vertex is at negative 1, negative 3. We now need to find a. Well, another way of writing f of x is y. I know a point, another point on the graph where I can that I can plug in for x and y. This point right here is at 0, -1. If I plug in a 0 for x and a -1 for y now, I can solve for a so that I can write the vertex form of this equation or of this graph. So I'm going to do that. I'm going to plug in a -1 for y, a 0 for x, and then solve for a. So that's going to give me -1 equals a minus 3. To get the a by itself, I'm going to add 3 to both sides, and that gives me that a is equal to 2. That means then that my function is going to be f of x equals 2 times x plus 1 squared minus 3. Are there any questions about how we came up with that equation just from looking at the graph? You start with the vertex form of a quadratic. Once you've identified what the vertex is, plug in those numbers for h and k. Then you simplify that and then plug in another point where you know x and y and use that to solve for a. Once you know a, you've got numbers that you can plug in for a, h, and k, and that gives you your equation for your quadratic function. In example 4, we're asked to use the vertex formula to write this function in vertex form. This is the general form, and I want to write it in vertex form. Well, the first thing I need to do is find the vertex, isn't it? How did we say we found a vertex if our equation is in general form? We use the fact that the vertex is equal to -b over 2a, f of -b over 2a to find the vertex. Well, it would help if I could identify what a, b, and c are here. Really all I need is a and b, but it doesn't hurt to identify. What is a? What is b? And what is c? When we find our x-intercepts using the quadratic formula, we're going to need to know all three of those, so it doesn't hurt to look at those now. So to get the x value of the vertex, I need to figure out what -b over 2a is equal to. Well, I'm just going to drop in these numbers. That's going to be -12 over 2 times 3. So that's -12 over 6, and -12 divided by 6 is 2, -2. Now I know the x value of the vertex. I got to find the y value, and how I find the y value is I find f of -2. So I go to my function, and in place of x, I'm going to drop in a -2. -2 squared is 4 times 3 is 12 minus 24 plus 7. So 12 minus 24 is -12 plus 7 is -5. The y value of our vertex then is -5. So now we go over and we use the vertex form of the function f of x equals a times x minus h squared plus k, and we drop in the numbers for h and k. H is -2, k is -5. So that gives us f of x is equal to a times x minus -2 squared plus -5. Now we just want to clean this up, and that's going to give us f of x equals a times x plus 2 squared minus 5. Now we need one more point on this quadratic function so that we can solve for a. An easy point to get is your y-intercept. To find the y-intercept, remember we just plug in 0 for x, and when I plug in 0 for x, what is y? 7. We're going to use the point 0, 7 to help us solve for a. I'm going to plug in a 0 for x and a 7 for y. So that gives me 7 equals a times 0 plus 2 squared minus 5. 0 plus 2 is 2, 2 squared is 4, so this becomes 4a minus 5. I'm going to add 5 to both sides, and that gives me 12 is equal to 4a. So what is a equal to? 3. Divide both sides by 4, and you get a equals 3. Now I can use this to write my final equation, and my function is going to be f of x equals 3 times x plus 2 squared minus 5. There is a bit of memorization that has to happen here. You've got to memorize this. And if you do all the homework and work with it enough and write it down every time you use it, it'll help you memorize it. But does the process make sense? If you're given the general form, your first step is to find the vertex. Once you know the vertex, put it in the formula. Once you put it in the formula, find another point. Usually the y-intercept is an easy one to find. solve for a, and then you can write your equation. Do I need to write those steps down? So these are the steps for converting the general form y equals ax squared plus bx plus c to the vertex form y equals a times x minus h squared plus k. The first thing you want to do is find the vertex. And this is what you use to find the vertex. The x value of the vertex is negative b over 2a. Once you know what the x value is, plug it back into the function and solve for y. And the function I'm talking about is this function right here. Once you've identified h and k, you want to drop them into this vertex form, put in the numbers, and then simplify. By simplify, I mean if you have subtracting a negative, change it to a plus. If you have adding a negative, make it a subtraction. Then you want to find another point on your graph. Usually the y-intercept is an easy one, and plug those numbers in place of x and y from that point, and then solve for a. And then finally you write the vertex form with the numbers that you found above plugged in for a, h, and k. You just plug in a 0 for x and solve for y. If you need that step written down here, how you find the y-intercept is you plug in a 0 for x and solve for y. But look, if you have this function, that constant term is going to be your y-intercept, but the x value is 0 at your y-intercept. In example 5, I ask you to go the other direction. Here I give you the vertex form and I want you to write it in the general form. This is actually easier. All you do is you FOIL this out, distribute the negative 2, and then combine like terms. You just follow your order of operations. So we're going to start with f of x equals negative 2 times, when you square something it means multiply it by itself, so I'm squaring the x plus 2. I'm going to write that as x plus 2 times x plus 2 and then subtract 3. So I'm going to FOIL this out, meaning multiply my first terms together, my outside terms together, inside and last. And that's going to give us f of x equals negative 2 times x squared plus 2x plus 2x again plus 4 minus 3. Following the order of operations then, I'm just going to distribute this negative 2. No, I'm not. What am I going to do first? I'm going to combine my like terms first. And that's going to give us f of x equals negative 2 times x squared plus 4x plus 4 minus 3. Now I'm going to distribute the negative 2, and that's going to give me f of x equals negative 2x squared minus 8x minus 8 minus 3. Once again, I have like terms that I can combine, and I end up with my final answer, f of x equals negative 2x squared minus 8x minus 11. And that would be our final answer. So if I give you the vertex form, you can write the general form, and if I give you the general form, you can write the vertex form. They each have their strengths. The vertex form is easier to use to spot the vertex. The vertex for this function would be what? Negative 2, negative 3. This form, though, is easier to spot the y-intercept. What would be the y-intercept of the function? Negative 11. So you see how they each have reasons for existing. There is another way to go from the general form to the vertex form, and that is by completing the square. Have y'all heard of this before? We teach y'all how to solve quadratic equations using this. This is actually a very handy skill to have, especially by the time you get into calculus. Most of my students forget it. And in Cal 2, I have to reteach how to do completing the square. It's kind of frustrating as a teacher, but I understand it because you guys have slept since you've seen it. So do your best to remember it. The way that we complete the square is we try to find a constant that we can add to the x squared and the x term so that we can write that trinomial as a perfect square. The constant that we end up adding is half of the middle term squared. I'm going to write out the steps for completing the square, and then we're going to work through a problem where we actually do it. Your first step is to make the leading coefficient here 1, and how you do that is by factoring in a off of the first two terms. We're not going to worry about the constant term. We're just going to let happen to it whatever's going to happen to it. Step 2 is to add half of b squared to the x squared and the x term and subtract the same value. So we want to add half of b squared to the x squared and the x term. If I've got those terms in parentheses with an a on the outside, I want to subtract off that same value over here so that I have a net gain of 0, but that constant that I added here was multiplied by a, so I've also got to multiply that by a as well over here. I don't normally write this step. I'm probably going to erase this, so write it down if you think you need it. When we go through an example problem, I'll point this out again. Now you're left with a perfect square trinomial, or a trinomial that will factor into a perfect square. You want to factor it. So you're going to factor. The resulting trinomial will factor into x plus b over 2 quantity squared. Then you've got your vertex form. So we've got two problems here in example 6 that we're going to use completing the square on in order to write them in vertex form. This is another option or an alternative from the steps that I gave you before on how to write these in vertex form. On A, we're lucky. Our leading coefficient already is 1. So I have f of x equals x squared plus 4x, and then I'm going to add something here so that this factors into a perfect square. What is it that I add here? What is b in this problem? B is 4, so half of that is 2, and then I square that and I get 4. So I'm going to add a 4 here, but if I add a 4 to have a net gain of 0, I also need to come along and subtract a 4. Do you see how the net gain here is 0? But now that guarantees that this will factor into x plus 2 squared, and then I just combine these two like terms, minus 5. So my vertex here is going to be where? At what point? Negative 2, negative 5. What's my x-intercept? I'm sorry, my y-intercept. The y-intercept's at the point 0, negative 1. You get the y-intercept from the original function in the general form. See, if I were to plug in a 0 right here for x, that would give me 2 squared. 2 squared is 4. 4 minus 5 is negative 1. This one was easier because the leading coefficient already was 1, and you end up adding and subtracting the same number, what clearly looks like the same number. On B, it's a little more difficult because our first step here is to factor out the half off of the x squared and the x. When I factor out a half off of the x, what number do I have to put right here? It would be a 2x right here. Because if you were to distribute that a half back through, you need to get back where you started. So a half times x squared is a half x squared. A half times negative 2 is negative 1x. Do you see how that works? The way that you do it is you take whatever numbers here, in this case that would be a negative 1, you divide it by a half, and that's how you get this number here. So that's negative 1 times, when you divide by a half, it's the same thing as multiplying by 2. You get a negative 2, and that's how you get this number right here. All of this was for step 1, factoring out that constant off of the x squared and the x terms. Now I need to come along and I need to add a particular constant. The constant that I add is half of b squared. For this problem, b is now negative 2. Half of negative 2 is negative 1, and negative 1 squared is 1. My net gain here, though, was not 1. It was 1 times the half that's out front. So over here I've got to come along and subtract what? Subtract a half. Don't subtract the 1 because that 1 is multiplied by the half. This is the part that most people end up forgetting. If you have a constant out front, when you add a constant inside the parentheses, that constant term is also being multiplied by what's out in front of the parentheses. So my net gain here was a positive a half, and to zero that out I have to come along and subtract a half out here. Now I'm ready to factor this, and I end up with f of x equals 1/2 times x minus 1 squared, and then 2 minus a half is 3/2, and that you could get on your calculator. Do you see why this was a minus 1? B, remember, was a negative 2. Negative 2 divided by 2 is negative 1. What's the vertex for this function in part B? This is in vertex form, so what's the vertex? Remember, it's ax minus h squared plus k, where the vertex is hk. Remember, I said the negative is part of the formula. The negative 2x right here, when I factored it, the resulting trinomial that I have right here by adding that particular constant factors into this. So I just factored this quadratic or this trinomial into the perfect square of differences. It's going to take some time and playing with this to get comfortable with this. Where's my y-intercept? Very good. And you would look at the original problem to get the y-intercept. The whole reason why we look at how to find a vertex and an axis of symmetry and these intercepts is so that we can graph the functions. When you're sketching a parabola, it's important to determine the vertex, the axis of symmetry, and whether the parabola opens up or down. We can use this information about the vertex, axis of symmetry, and the y-intercept in order to, and how the graph opens in order to sketch the graph. So in example 7, I want you to graph each of the quadratic functions. In order to graph these, we're going to need to start with a grid. Well, actually, before I draw my grid, let's identify where the vertex is. Where's the vertex here? What's my axis of symmetry? Do I just write -1? And will this parabola open up or down? Now I'm going to draw my grid. Whenever you're sketching in a quadratic, you start by plotting the vertex. The vertex we said is at -1, 2. My axis of symmetry is this vertical line right here. And I need another point to the left or to the right. I know it's going to open down. This would be sufficient to get a rough sketch of the graph, but I would like to draw a better sketch. What would my y-intercept be? How do I find my y-intercept? It's at 0, 2? No, it's not. I plug in a 0 for x. What do I get for y? 0. My intercept happens to be at this point right here, and because of symmetry, I have another point right here. Now I'm ready to sketch in my graph, and it looks like this. My graph isn't scaled perfectly, so it looks asymmetrical, but in a perfect world this would be symmetric. If you did this on graph paper, it would look perfect. How did I find that y-intercept? I don't just look at it like this whenever it's in this form. I actually have to plug in a 0 for x and solve for y. So that's how I knew that my y-intercept was right here at 0, 0. And then because of symmetry, if that point is 1 unit to the right of the axis of symmetry, I have another point that's 1 unit to the left of the axis of symmetry. You need a minimum of 2 points to graph a straight line. You need a minimum of 3 points to graph a parabola, as long as one of those points is at the vertex. On part B, we need to begin by finding our vertex. This is not in the vertex form, this is in the general form, so the first thing I need to do is find the vertex. Do I want to find the vertex using -b over 2a, f of -b over 2a, or did y'all like putting this in the vertex form? Which method do you prefer? You like the vertex form? So you want to complete the square on this. I'll do it. This is easier, but I'll do it. We're going to do it. So h of x is equal to, I'm going to have to factor out the 1/2. That gives me x squared minus what? 4x. Then I need to come along and add what to make this a perfect square? 4. But I didn't add 4, I added a half, which means I added 2, which means I need to come out and subtract 2. My net gain here was 2 because 4 times a half is 2. So I added a value of 2. I need to come along and subtract a value of 2. So that's going to give me h of x equals 1/2 times x minus 2 squared minus 2. Y'all sure y'all like this method better? No? Let me show you how to find the vertex using this. This is how easy it is. What is a in this problem? A equals 1/2. What is b? -2. So -b over 2a is equal to the opposite of -2 over 2 times 1/2. The opposite of -2 is 2 over 2 times 1/2 is 1. The x value of the vertex is 2. Well, that's what we got there. So far, so good. How do I find the y value of the vertex? I just find h of 2. Once you get the x value, to get the y value, you plug that x value in place of x. So that's going to be 1/2 times 2 squared minus 2 times 2. 2 squared is, half of 4 is, and 2 minus 4 is, there's the y value of the vertex. I don't care which method you use, you need to be familiar with both. So we have a vertex at 2, -2. What is our y-intercept? We plug in a 0 for x, I get 0 for y. That should be enough. Will my parabola open up or down? Opens up because the leading coefficient is positive. So I'm going to start this graph by plotting the vertex. I have a vertex at 2, -2. My axis of symmetry is where? So I'm going to have an axis of symmetry along this vertical line here. I was told my y-intercept was at 0, 0. Well, I wasn't told that. I figured it out. Where do I have another point because of symmetry? 4, 0. And yeah, at 4, 0 because of symmetry. If I were to fold this point over across that line, it has to land right there at 4. Now I've got 3 points. I just play connect the dots, and we've graphed another parabola. So you begin by finding the vertex and intercept, axis of symmetry, plot the points, sketch the graph, and you're done. Now let's look at some application problems. I told you in the beginning that parabolas have maximum values and minimum values. We use that fact to solve problems where we need to find a maximum or a minimum of something. So sometimes when a quadratic function is used in applications, the vertex provides important information. The reason is that the y-coordinate of the vertex is the minimum value of f of x if your graph opens up, and it's the maximum value if it opens down. In example 8, we're told that a rancher is fencing a rectangular area for cattle using the straight portion of a river as one side of the rectangle, because we all know cattle can't swim. If the rancher has 1,800 feet of fencing, find the dimensions of the rectangle that give the maximum area. So here's the length of the area he's fencing. Here's the width. We need 2 sides of W, but only one of L. We're told something about the amount of fence that he has. That's called the perimeter. Where the fence goes is on the outside edge. So our perimeter is equal to 800 feet, 1,800 feet. In this particular problem, with the way the picture is drawn, the perimeter is also equal to 2 times W plus L. So we end up with 1,800 equals 2 times W plus L. We were asked to find the maximum area. If this is the region that I have fenced in, how do I find that maximum area? Length times width. The area is equal to length times width, and I want to maximize that area. Well, the problem is I've got 2 variables here, the length and the width. What I can do is find the length in terms of the width by subtracting 2w from both sides here. When I do that, that allows me to write the length as 1,800 minus 2w, and that's what I can plug in place of the L right there, so that I can get the maximum area. Now my area function looks like this. Area is equal to 1,800 minus 2w times w. If I were to distribute the w here, I end up with the area is 1,800w minus 2w squared. What type of equation is this? It's a quadratic equation. Will that quadratic equation open up or down? This is a quadratic equation that opens down. It's a quadratic function that opens down. And that means that the maximum value will occur at the vertex. So guess what I have to do? I have to find the vertex of this quadratic function. So I have a equals. Some people like to write their quadratic term first, or the square term first. You could write a equals negative 2w squared plus 1,800w. If you're going to find the vertex with your function written in this form, do you want to use the negative b over 2a, or do you want to complete the square? Have I won you over to the negative b over 2a? Alright, so the x value of the vertex is going to be found by looking at negative b over 2a. What is b in this problem? It's what the w is being multiplied by, the 1,800. And then a is negative 2. So 1,800 divided by, negative over negative is positive. 1,800 divided by 4 is what? This is where calculators come in handy. I'm not doing it. 450. That's the x value of the vertex, which is actually the length of the width of this perimeter. The y value of the vertex is the maximum area. Oh, but we weren't asked to find the maximum area. We were just asked to find the dimensions. This 450 feet is the width. How do I find the length that maximizes the area? Right here is my formula for the length. The length is going to be equal to 1800 minus 2 times W, which is 450. And what is that going to give us? 900. So the dimensions to maximize the area are going to be 900 feet by 450 feet. What is the maximum area? How many square feet? How would you get that? Just multiply length times width. I didn't ask you for it. I'm not going to ask you for it. Example 9. A baseball is hit straight up with an initial velocity v sub naught of 96 feet per second and leaves the bat with an initial height h sub naught of 2 feet. Anytime you're given these motion problems, you're going to use this. S of t is, S is what we use for position of an object in space, is equal to negative 16 t squared plus v sub naught times t plus h sub naught, where v sub naught is an initial velocity, h sub naught is an initial height. When I say naught, it's N-A-U-G-H-T, like it's a subscript of 0. It's an old-fashioned term. This 16 has to do with the fact that the acceleration due to gravity is negative 32 feet per second. If we were working in meters instead of feet, I think this is 9.6 here instead of 16. But this is something that you should know. So on part A, we're asked to write a formula that models the height of the baseball after t seconds. All we do is we plug in the numbers that they gave us in the problem for the initial velocity and the initial height. So for part A, we were told that the initial velocity was 96 feet per second and the initial height was 2 feet off the ground. So there's our function that models the height of the ball after t seconds. Part B of this question asks, how high is the baseball after 2 seconds? Well, how would I find how high the baseball is after 2 seconds? Plug in a 2 for t. And this is why God gave us calculators. 130. So after 2 seconds, the ball is 130 feet above the ground. Part C says find the maximum height of the baseball and then support your answer graphically. So the maximum height is found by looking at what? The vertex is how we get the maximum height. If this is our function right here, how do I find the vertex? A is negative 16, B is 96, C is 2. I don't really need the 2 for this. So to find the vertex, I'm going to use negative B over 2A. So that's going to be negative 96 over 2 times negative 16. And tell me what we get for this. I get 3. So it's negative 90. You've got to put the denominator in parentheses because there's 2 terms. You want to divide 96 by 2 times negative 16. So it looks like at 3 seconds, we've reached our maximum height. We were asked to find that maximum height. The maximum height then is going to be equal to S of 3. And S of 3 is negative 16 times 3 squared plus 96 times 3 plus 2. And I'm going to do this on my calculator just because I don't want to do the arithmetic. So I'm going to hit y equals, and I'm going to graph my function. We have negative 16 t squared, I got to use an x, plus 96 t plus 2. And I'm going to let my window go from 0 to 6. Let me do 0 to 10. The x scale is fine. The y is going to go from 0 to, let's say, 200. And see if that gets us a good picture. Oh, we get a good picture. That looks like the trajectory of a baseball, does it not? Okay. To find that maximum height right there, one way I can do it is I can hit second, calculate, and I already know the x value is going to be 3. So I just put in a 3 for x, and I get my maximum height is 146. And here's my graphical support.